Hello, my name is Hannah Edwards, and this is my artificial blood vessel benchmark assignment. So to start off, a little background: the human body is a ever-changing, unpredictable environment, and so things happen. And a common situation that happens in the body is a blood vessel being blocked and causing damage to that blood vessel. And so a way to approach that and a way to fix that could be replacing with another blood vessel in another part of the body, or could be using a artificial vascular prosthesis. And so a lot of research is being done for artificial blood vessels, and the tricky part is finding an appropriate material to substitute and replicate that connective tissue, that those cells that make up the blood vessel. And so there's a lot of things that affect the material to choose. That can be where the blood vessel is located. There's arteries, capillaries, aortas, which are in the heart. And so they vary in size, and as well as it can depend on the human being themselves, their weight, their exercise. That all depends on flow rate and the healthiness of their blood vessels. And so that all is taken into account when researching materials for replacements of blood vessels. And so the research that I have concluded, I have come to the conclusion that the values I used for my flow simulation and to replicate a blood vessel is the average flow rate for an adult male is about 4 miles per hour, which equals out to 0.0129 kilograms per second. And that is actually the value I used in my flow simulation. The average diameter for an artery is 4.6 millimeters. I used an artery because we are dealing with the heart, and the aorta is very large, and so an artery is more similar size to the other capillaries and veins and stuff like that, but it is on the larger side. And the blood vessel wall thickness is about 1 millimeters. Again, all of these things can vary, but these are the values I chose. And blood temperature for blood for a human is about 310.15 Kelvin. And so through my research, I came to the conclusion of these three biomaterial options. The first one, this is going to be interesting to see how I pronounce them, polytetrafluoroethylene. Sound pretty good. So this first choice is a synthetic fluoropolymer. It has nanofibrillar structure, which is suitable for cell cultures. It is friendly to the environment of the human body, pretty much. It's got porous membrane, and it's got a lot of great characteristics, mechanical properties: flexible, tough, strong, resistance to chemicals, high melting point. And what's also neat is when placed in the body, the endothelial cell makes up the blood vessel wall. It's a graft. It's the extracellular matrix is what the majority of the blood vessel wall is called. And so with this biomaterial, endothelial cell adhesion, as it's in the body, it starts to attach to, or the endothelial cells attach to the material and kind of make the environment welcome it as its own blood vessel. So it's pretty neat. And the second choice I did for my biomaterial is polyethylene terephthalate. That one is going to be, again, strong, stiff, synthetic fiber, resin polyester polymers. Again, all of these are going to have very similar characteristics and mechanical properties because we are trying to do the same thing with these three biomaterials. So all these properties I'm speaking of are all compatible for a blood vessel. Polyethylene, this polyethylene is less expensive, which is appealing, as well as it's got resistance to hydrolysis, which we do not like that. And it can be woven and grafted as well as the one above. And My third biomaterial is thermoplastic polyurethane, which block copolymers, high melting point. It's elastomeric nature, and again, a great replacement, great mechanical properties for a blood vessel. And so the economics background is for polytetrafluoroethylene. It's about $3,000 per metric ton. For the polyethylene tetrafluoroethylate, it's about $1,292 per ton. I apologize. And thermoplastic is about $2,400 per metric ton. And that will be discussed towards the end, the economic reasoning. So these are my solid work properties. Researched the properties because I needed them to mimic the material I was looking for. And so these are my flow simulations. So all of these pictures are going to be the 1 millimeter length long blood vessel. I put a mass inlet flow, mass flow rate on one side of the lid, and then I put a static pressure on the other side of the lid. And what I chose to do was chose to show a cut plot of the velocity, just to kind of show that it doesn't change throughout each one. So I'm doing the same to all blood vessels, as well as the surface plot of pressure, because the way the material reacts to pressure is important, because that's how it reacts, and we need to understand that so that we can understand the mechanical behavior and see which material is the best. So they all look the same, which is expected. It's only 1 millimeter of a blood vessel, and the velocities do not change, and they're very similar. As you can see, this is the polyethylene tetrafluoroethylate in the bottom left, and it does have it's got a little red, a little different coloration, but that can't be really used for much. And so this is going to be the 10 millimeter flow simulation analysis. Again, the velocities do not change. And it goes from order of as I described them, left to right. And as you can see, the last two have very similar reactions to the pressure. The pressure is not as heavy towards the beginning, and it's a lot more calmer as the I'll just say the PTFE. The first one I described, that is going to be the first picture, and it does have a little more of an effect in the beginning, and does kind of more affected by the pressure. And so this is the flow simulation for 100 millimeter blood vessel, and as you can see, again, the velocity is a little different for the first one. I think that might be human error, because it should not be changing, as well as the pressure for the PTFE is a lot more elongated. The pressure's expanded through. It does start where the inlet flows, but it relieves pressure as the blood flows, versus the last two have very similar effects, where there's a very high pressure and effects to the material for more than half of the blood vessel. And so with that, I will talk about these numbers in the next slide, but these are a comparison between pressure, velocity, and shear stress. So the shear stress is really what I'm going for. That is going to be the effects to the material, the ability of the material to deform, and we do not want that. So I'm basing my comparison off of my shear stress numbers. And so it shows the minimum shear stress, the maximum shear stress, and the average shear stress for the blood vessel. And it goes through each material and each length. And so the important numbers that I'd like to discuss are the 10 millimeter long blood vessel. The 1 millimeter long blood vessel had very similar numbers. The only difference was 0.0001 off. And so I'm talking about the last two. And so for ePTFE, it's about 8.6. And then for the other two, 9.3. And then for a 100 millimeter long vessel, it's about 4.5, and the other two, 4.7. So what I chose to do for a comparison, because the PTFE had the lowest, and I had 3 values, I chose to do the percent difference for the lowest compared to the other to show the difference and see if it's a significant difference to base my material off of. So the percent difference for the 10 millimeter PET to the PTFE was about 8%, from the PTU, about 7.6%. Percent difference for 100 millimeters, about 5.6 for PET, and PTU is about 5.36%. And so these are pretty significant percent differences when it comes to the human body. Biocompatibility, biomaterials, there's definitely less wiggle room, less room for error because of the reaction a human body can have. The slightest change, the slightest irritation can cause damage, and that is very, very bad. And so that's just a little note, but economical reflection. I'll go back really quick, keep going. So based off of these numbers, based off of my flow simulation images, I have chosen the polytetrafluoroethylene. I think I said that correctly. Based off of the numbers, there is a significant difference between the effects, the shear stress on that material versus the other materials, and as well as the economic reflection. It is the most expensive per ton, but I find it very significant to break it down to how much is going to be used. You're not using a ton every time you build a blood vessel, and so a ton can be broken down into grams, and a blood vessel isn't even a gram, and so it's less than that, but that's as broken down as I could get. So there's 907,185 grams per ton. And so I divided that number by the $1,000 US. And I got pretty much the portion of dollars it would cost for a gram, which again, it's less than that per blood vessel. And so it's about $0.0033 for PTFE, $0.0014 for PET, and $0.0026 for TPU. And with these numbers, when you put it in that perspective, there's a very small difference between the numbers. And over the years, you're not using them consistently. It's per situation. And so I think when it comes to the human body, it's very important to make the right decision and pick the right biomaterial that will affect the body successfully. And it is important and it is ethically right to choose better than cheaper when it comes to the human body, because obviously death is the worst outcome, but there's a lot of terrible things that can happen, especially working with blood vessels. We got to get blood supplying to all parts of our body so our brain can function and work. And one little mishap can lead to a lot of mishaps, as I'm sure we all know. And so with that being said, I think it is worth, when broken down in this matter, to spend the money for the PTFE. So in conclusion, with my analysis, I think the ultimate biomaterial I have studied was the polytetrafluoroethylene. I think it is the best material to use for an artificial blood vessel, and that will be what I use. And so here are my resources. I hope you enjoyed the presentation, and I hope you have a great holiday season. Goodbye.